No, we should hear a recording process.
Like recording in progress.
Okay, then I use my audio here, and we all. Okay. We get ready.
Oh, and now they're.
Okay, we try this way, and then see how it goes. Like,
Okay.
the only problem is that we cannot get the audio if someone is speaking.
Yeah, if somebody
later on.
Yeah.
Okay. Okay, sorry for the slow start. So today our speaker is Nuria Torres Alba. She's a Gecko Fellow at the University of Virginia in Charlottesville in the US. Previously, she got her PhD from the University of Barcelona in 2019. Then she had a postdoc at Clemson University from 2022 to 2024 before moving to Charlottesville. She's working in AGN and their surroundings from X-ray and other wavelength, focusing on near galaxies and quantum theta AGNs, and also in the interaction between jets and their surroundings, gamma rays, and interaction with jets and environment in general. And the stage is yours.
Thank you. Yeah. So today I'm going to be talking about this work that we started at Clemson University, mostly in collaboration with Stefano, who you all know. It is about using obscuration variability in nearby AGN to try and say something about the AGN torus. Was this me? No, then now it's working. Okay, so the general structure of an AGN, we have a supermassive black hole, which is surrounded by an accretion disk, which is going to be thermally in the UV to infrared range. This whole structure is covered by an obscuring torus, which is only obscuring certain lines of sight. Now, the X-ray emission is produced from a very compact region near the supermassive black hole, which we call the corona. And in the corona, the photons of the accretion disk get inverse content scattered into X-ray energies. The resulting emission in X-rays is just in the simple shape of a power law. But that's only if we're looking through the unobscured direction. When we look through the torus, what happens is that the softer photons, or the lower energy X-rays, get obscured, they get absorbed. And the exact shape of this turn over here is very tightly related to the exact amount of obscuration in our line of sight. Now, in this way, when we have an unobscured AGN, we have the simple power law I was telling you about. But as we increase the column density, or amount of material between us and the AGN, slowly we reduce the emission in the softer X-rays. We get pushed more and more and more. In a way, as I said, this exact shape, curvature, and the start of this turnover is very tightly correlated to this measurement of NH, or column density. So X-rays are a very nice tool to very precisely measure the exact amount of obscuration in our line of sight when we look at an AGN. Something that is generally relevant or important is that when we only have what we call soft X-rays, so below 10 keV, sometimes we can miss some vital information that is useful to break the degeneracies in the spectral fitting. So generally, we would like to have Nuster in this data range to try and get the best measurement of obscuration possible, particularly when we have very highly obscured sources, or those we call quantum thick AGN, when the column density is above 10 to the 24 per centimeter square. What we have is essentially a very extreme suppression of X-rays below 10 keV. So then it's very hard to say anything about those, the obscuration or anything else in the AGN without the high energy look. So our current understanding of the AGN torus in the past few years has shifted from the first, homogeneous simple picture to knowing that this is incorrect and it is most likely patchy or clumpy. Now, this comes both from infrared data fitting and particularly more interesting for this talk from X-rays, because we have seen this obscuration in the line of sight that I was talking about change between one observation in X-rays and another observation taken at a different time. And these changes can happen in timescales as short as less than 1 day and as long as years. So to show it, I say here in real data, but in fairness, it's a simulation of the full band, Nuster and XMM. This is a simulated spectrum for the same source, same exact properties of the X-ray emission, except for the obscuration in the line of sight. So essentially, we have two spectra that look like this. We can fit them and recover a value of obscuration versus, in this case, the photon index, so the inclination of the original power law. And we can recover that these are very different at the 3 sigma level. So this is, as I said before, a very good tool to measure precisely that. And we do it exactly in this way. Now, why do we care about this? Why do we care about this obscuration? Why do we care about the fact that it can sometimes be different? Well, this is because past results have shown some peculiarities, I would say. For example, any work so far that has looked at relatively small samples of sources, and I'm talking, 10, 20 AGN perhaps per article, has seen systematically that less than 50% of AGN are found to be obscuration variables. But now if we know that the torus is clumpy, why is it less than 50% of AGN? Is this normal? Is this expected? Or should we perhaps be seeing something else? And this is a question that at the moment we cannot answer. In fact, if we consider, the starting point of things that we cannot answer, we know remarkably little about obscuration variability. We don't know how many AGN in the near universe are known to be obscuration variable. We don't know the typical range of variability. We don't know the typical timescales. We know extremely little about this process, apart from the fact that it has been seen to happen in some sources. We don't have anything statistically significant to say about it. So in this sense, it's already worth exploring. Now, something else of peculiar interest is that this methodology has been used to say some very interesting and precise things about the AGN torus. So here, I'm going to show you the results of a work that did, semi-continuous monitoring of AGN in X-rays with RXTE some years ago. What you're seeing here is at the top panel, just a band ratio. So softer X-rays against harder X-rays. And then this gets translated into the 3 lower panels into just obscuration, or NH, as a function of time. The 3 panels have the same data points, and the curves are just different attempts at fitting this obscuration variability with the shape of an object essentially crossing into our line of sight. In the first attempt here, we have a single uniform sphere, or 2 different uniform spheres passing one after the other, pretty bad fits. Then there's an attempt with a double beta profile, so 2 spheres, but not a uniform profile, a different decay of density with radius. And finally, the last one, which is the best fit, is a uniform density shell. So essentially like a bubble, kind of empty on the inside and thicker at the edges, right? That produces the best fit. Now, if we actually had a lot of data like this, of a lot of eclipses of clouds into our line of sight around AGN, we would be able to truly characterize how the material that forms this torus that surrounds the AGN looks like. However, this is not the case, because in X-rays, it's extremely complicated to get very long-term continuous monitoring campaigns. That's just not how X-ray observations work. You typically get pointed observations, rather short, separated by years. In fact, the most extensive study that has done something like what I am showing here is the study of Markowitz in 2014, and it only monitored 8 objects semi-continuously for 17 years, only saw 12 individual full eclipses. Now, if you have to separate these between Seyfert 1s and Seyfert 2 galaxies, so more obscure, less obscure AGN, you are left with 8 events and 4 events. With these, what people have done is create a probability density function of observing an eclipse or a cloud passing in front of you as a function of the duration of this eclipse. Now, this is obviously very biased because it's 4 events and 8 events, right? It's not statistically significant. Yet this is the best thing we have at the moment. That is a large sampling. And therefore, it is currently being used to calibrate X-ray clumpy torus models. So of course, there is room for improvement here, right? So essentially, what we want to do with this general obscuration variability project is make use of the vast amount of data that is available in the archive regarding AGN, in which we have, what I was saying before, very separated, randomly taken observations, but oftentimes of more than one observation per AGN, spanning perhaps the time differences of up to 20 years, which is the archive of Chandra and XMM, for example. So in the context of this project, we have 3 different sub-projects. One of them is based on fitting archival observations available for a sample of about 100 moderately obscured AGN that was initially analyzed by one of our students at Clemson, Shuri Zhao, graduated already quite a while ago. And it's a good sample because it has a lot of sources, 100. They all have Nuster. They all have at least one soft X-ray observation. And what he observed for a lot of them is what I'm showing exactly here. When you overlay them, they don't match because they're not simultaneous. They're just randomly taken from the archive. So you can find variability between one and the other, and you can try to fit them to know if this variability is an intrinsic luminosity change or it's actually a change in obscuration. And we can do that for all of the observations available in the archive for all of these, because 80 of these sources actually have more than the 2 observations that he initially used. So there's plenty of margin to do things here. The second project is based on capitalizing the archival, the Chandra archive, using harness ratios. I'll go more in depth into it later. We'll have about 80 AGN as well, with a lot of observations, and it includes both obscured and unobscured AGN. The final project is about content-thick AGN, this very obscured AGN. This project is mostly led by Stefano and based on obtaining new monitoring campaigns. And I'm going to be skipping this one in favor of having Stefano explain his work someday. So focusing on what I was saying about this content-thick sample, what are we exactly doing with this 100 source sample? Well, what we do is we put together all of the observations available in the way that I'm showing here. So you can already see, if you look at the observation at the very top, which is kind of orange, and the one at the very bottom, which is kind of purple, you can see that they have very clearly different curvatures as they go up, right? This translates to a very different measurement of obscuration. So we fit all the observations simultaneously, and we get this sort of profile for obscuration curves of all the data points that are actually available. We have done this so far for a lot of sources. In fact, for the 30 sources in which our student, Shuri, initially found some kind of variability. So we have started from an admittedly biased sample, trying to find obscuration variability in these first 30 sources. And this is separated into the papers that I'm describing here, a pilot project that was done by Andrea Picciotti, a PhD student, what used to be a PhD student in Clemson, actually her undergrad here. And then her and I together published the graph of the project recently. We have also monitoring campaigns, and there was also an in-depth analysis of a single source done by Dhruv Sengupta, who was a PhD here until very recently. At the moment, we have analyzed more than 150 different observations, and we are working on the rest of the sample that was initially not found to vary, because of course, eventually we want something unbiased. So I'm just going to present a few of the most interesting or preliminary results of this analysis. And I think that the biggest thing we've found so far is that in this full sample of 28 sources that were selected because we thought they were going to be variable, only 28% of them we can claim confidently that they're obscuration variable. Now, this begs the same question I asked before. Why? If the torus is patchy, why aren't we finding more obscuration variability? Do we need to take a second look at the structure of this material to be able to explain this behavior? Something else that I think is particularly interesting is the dichotomy in the behavior of different sources. The plots that I'm showing here are showing you the obscuration as a function of the time that has passed since the first observation for that source. This is spanning 10, 20 years for these sources. These two sources, on principle, they're both C42 galaxies, so obscured AGN. They have a similar enough average obscuration, but they behave very, very differently. Now, if we ignore all these horizontal lines, which are not relevant to the talk today, and you just look at the data points vertically, we're using multiple models. That's why there's multiple data points at each time span. They all agree, which is great for our project. You can see that the source on top varies very much between around 20 times 10 to the 22 and 100. The other source, however, is permanently staying, and this is in log scale now, between 15 and 22 in the time span of 10, 15 years, even though we have 10 individual observations. So the question here to ask is, what are the odds, if this material is clumpy, that I take 10 randomized observations throughout 15 years, and I always see essentially the same obscuration? Can we actually explain that with a toroidal geometry that is patchy? And we don't know. The answer to this question, we don't really know, but I find it a little suspicious. Now, something else that I think is also interesting when we have this simplified classification of is something variable, is something not variable, is that it kind of depends a bit on the number of observations that you have for a source. So this is one of the most extensive monitoring campaigns we have on Markarian 477. And I'm showing for the 15 observations available, confidence contours of the obscuration vertically and a cross normalization of flux, right? So either cross calibration between instruments or a genuine change in intrinsic luminosity. We don't particularly care in this context. Anything that is vertically separate is incompatible with having the same obscuration. So there's quite a bit of mixing, right? And here these lines from red to blue, they just show the time that you should follow to go from the first to the last observation. There's two panels because putting everything in one is very messy. But essentially the point here, the main point is that if you only had 2 observations for this source, your probability of finding this to be obscuration variable would only be 40%, even though it is obscuration variable. However, if you have at least 4 observations, this increases to a chance of 95%. So I think one of the things we want to do with this project eventually is be able to give a rather robust estimate of how many observations do you need to confidently say that 2 sources are behaving differently, that it's incredibly likely to vary versus very unlikely to vary, in order to properly classify things. And so finally, one of the most interesting results, I would say, is the behavior of the general behavior of the sound. So here, this is the probability, actually, of 2 observations of the same source having different obscuration as a function of the time separation between these 2 observations. And you see that there's a very strong dependence with the time difference between observations. So this is telling you something about the structure and the distribution of the material within the torus. Because not just any random structure and distribution of clouds is going to be able to reproduce this. For example, if all obscuration variability was coming from broadline region clouds, which have a crossing time that's shorter than a day, this should be flat instead of increasing. So there is information given here, right? Something else that we can also try to use is this plot, the average change in obscuration between 2 different observations of the same source as a function of the time span. Now, this is sort of the information, the general information we've gotten out of this first project. I'm also going to be talking about what we're trying to do with hardness ratios. Now, hardness ratios are very different to the very specific and complex fitting I was showing until now, which is a lot more precise. But hardness ratios are very, very quick. The only thing you're doing there is comparing the amount of counts of photons that you have in one band that is harder versus one band that is softer. Right? So it's, as the formula says there, hard counts minus soft counts over the total number of counts. So 2 observations that have different obscuration are going to have a different ratio between these 2. So one of my students, Isaiah Cox at Clemson, what he did was try to calibrate which are the ideal bands that we should use to try and target this obscuration variability for a range as broad as possible of obscuration in TGM. And he came up with these 2 band combinations. Now, the way that you can use this when applying it to archival data is simply you just plot the hardness ratio 2 versus the hardness ratio 1. Now, any data points that don't overlap there in space have a different obscuration, have a different spectral shape, essentially, which we're attributing to obscuration changes. So in this way, the red and blue data points are compatible with each other. This cluster of 3 data points here, all compatible with each other, and this one stands on its own. So this source has a bunch of observations, but only 3 different NH values throughout the time, or obscuration values. And in fact, he calibrated this against the results of the fitting that I was showing you before. So this is the result of the proper fitting in this vertical column in the same colors, right? So the same 3 observations indeed resulted to have the same obscuration. These 2 resulted in having the same obscuration, and the same can be said for this one over here, right? So what he did with this, which as I said is a very quick method compared to spectral fitting, which needs to be a lot more supervised in these kind of nearby bright sources, is apply it to the whole of the Chandra archive of sources that have enough counts, of course. And these are, I would say, the 2 most important results of that work. What you're seeing here is just for each of the sources, the number of observations that each source has, and it is colored as a function of whether they are obscuration variable or not. The gray is not variable, the green is variable. So something that I think is very evident already in this plot is that there's a strong dependence on the number of observations that you have. And eventually, if you have enough observations, perhaps you will always find a source to be obscuration variable. So this goes back to the same questions of how many observations should we need to actually be able to do this kind of studies properly. That's what I'm showing here as well. So this is the variable fraction, so the number of sources that we find to be obscuration variable versus the number of observations, and this is a cumulative plot. You can see that there's 3 lines here, and this just depends on how strict we are when we consider the distance between this data point between errors, right? So you can impose that this distance should be higher or lower at different confidence thresholds. For the least strict threshold, which is this one here, I think we were a bit optimistic, so I wouldn't trust that so much. But the more strict thresholds agree quite a bit in the fact that this increases strongly with the number of observations, but perhaps could start to stabilize around here when you have 5 or 6 observations already and up to here. However, admittedly, we just don't have enough sources to be able to tell if this would actually stabilize into a population of genuine non-variable AGNs, or if it would eventually continue to increase monotonically. But in any case, the slope with which it does that, again, tells you something about the distribution of material surrounding the AGN. So how exactly, right? And this is, I would say, the final stage of the project, which is what we're striving to put together now. What we can do is we can simulate a distribution of material. I'm exemplifying one here. This is a top view of an AGN. The black hole is in the middle. Everything would be rotating this way. So if we put this up, we simulate it, we make all of these clouds rotate. What we can do is take lines of sight into the AGN with the same cadence of the data that we already have and compare the simulated controlled results with our actual data. And the data that we have needs to be able to reproduce, the model that we have needs to be able to reproduce the data, right? And in this way, we can constrain the distributions of material that make sense versus the ones that don't make sense. So in this sense, we need to be able to reproduce both very variable and very non-variable sources. And the question here would be, do we need a strictly different distribution of material to explain these two? Or would perhaps just a change in inclination angle be able to explain the difference? Perhaps if you look at John purely, there's more clouds, and therefore you always intercept a similar number, you don't see variability. Perhaps the ones that vary, they're just quite inclined, so you catch the edge of the distribution. Sometimes a lot of clouds, sometimes not. Then again, if you try to reproduce the patterns, not of individual sources now, but of the whole population, you can set some constraints on the average geometry and properties of the average AGN torus, right? And that's something that we can do with the 2 plots that I was showing you before, the dependence of variability with timescale and the dependence of variability with the number of observations. So finally, what we want to do now to improve these results that we have, which are interesting, but of course inconclusive at the moment, is first of all increase our sample, right? We have a sample of about 80 sources that have a lot of observations. We've only gone through about 28. We are now working into the analysis of the rest so that we have a much better sampling than the one we have now and more unbiased because we selected the first 28 in a biased way. Then we obviously want to do monitoring campaigns, and not just to have more sources and more observations, but also because there are some particular gaps in our time interval distribution between observations, because it's something we don't really have control over when we're using archival data. And finally, we want to apply this harness ratio method extended to the XMM archive, in which there's a lot more AGN with more counts because of the larger collective area of XMM. And finally, we are setting now this 3D model setup with which we expect to be able soon to say something about the torus geometry by using all of these data to calibrate. That's it. Thank you.
So 27, you're still plenty.
Yes, I thought I was so bad on time that I just went for it.
Sorry, I should stay here probably to check for remote questions, but okay, remote question.
So for the HR method,
Yes.
can you go back to the HR1 versus HR2? So
Yes.
the same source with the same image, will have very different HR if seen with XMM or Chandra, and
Yes.
even if Chandra 1 and Chandra 5.
Yes, it's so Chandra 1 and Chandra 5. Yes, what we did there in this particular work, we did not extend that to the work on the Chandra archive because it's it introduces error. We corrected for the differences for the shape of the collecting area. We did like band cuts into the spectrum and corrected the difference of collecting area between Chandra and XMM.
So it's not a classic hardness ratio.
Correct, exactly. So this is the Chandra hardness ratio, and the XMM hardness ratio is corrected into the Chandra hardness ratio. Now, as for the Chandra 1, Chandra 2, and whatnot, I actually have a backup slide on that here. So the Chandra collecting area changes significantly depending on the cycle that you are in, right? And of course, the XMM area would also have a very different shape in here. In order to not have to do this conversion for every single Chandra cycle, you know, we have to calibrate it for every single Chandra cycle. What we did is we opted to just ignore everything below 2 keV. So our hardness ratios, our bands, are all above 2 keV. And as you can see here, the area barely changes above 2 keV despite this strong degradation below. That's why we choose to not use the classic hardness ratio, which is 0.5 to 2 and then 2 to 7. And we're using essentially hard band hardness ratios on.
Check around the people here. There was a question over there. Yes.
Nuria, what is the lowest X-ray luminosity you are sampling?
The lowest X-ray luminosity we're sampling, not very low. I don't think I have a number for you at the moment.
Wow.
41 probably for very nearby sources, right? Because we're just using anything that's in the archive, and these are essentially flux cuts. But this is count cuts, so flux cuts at the end of the day for a lot of these sources. The sample is probably a lot more representative of a slightly higher luminosity than that, at least above 42, closer to 43, I would say.
I was wondering whether you have enough leverage in X-ray luminosity to observe any indication of correlation with the luminosity.
Not at the moment. We don't have enough sources, I would say. I would hope that once we finish the analysis of those 80 sources or so, we're going to have a certain range. Of course, we're going to have it oversampled in a certain area of luminosity and a bit undersampled at the extremes. But we're going to have enough, I would say, also particularly to try to correlate with intrinsic luminosity variability of the same source as well. Because there's some theories that would tell you is that material may be pushed in or pushed out based on the brightness of the AGN. So that could be a potential explanation behind the changes in obscuration. If you don't believe that the obscurity is, the classic torus, but something perhaps a bit more convoluted. And we would like to test for that too, eventually.
And I was wondering whether you are also looking at the WISE data, the coverage of the entire database WISE data for the same sources.
No, we are not at the moment. And it's something that I've been thinking about as well, because we're classifying sources a bit broadly, right, into variable and non-variable. Do they look differently at different wavelengths? I think it's a very interesting thing to try to take a look at. Do they have typically different WISE colors or, Spitzer spectra, whatever that we could try to find in that regard. If they do, that's interesting. If they don't, I think that's interesting as well, in fairness.
We have another question. Yeah.
I was wondering, and also related to this last point that you were mentioning, you say like the clear clues that the torus is clumpy come from the infrared.
Yes, there's a couple indications of that.
So I was wondering, for these sources, when you do a modeling that tries to reproduce the data, you will also look if it reproduces the infrared rate.
Yes, exactly. So I've been in contact with the creators of SCIRT, of the X-ray module of SCIRT, which is a radiative transfer code. We believe that we can use SCIRT to calibrate this geometry in X-rays. And then because you have this geometry and SCIRT itself is a radiative transfer code, you can put this geometry into SCIRT and be like, okay, give me the infrared spectrum. And then you can go and compare with the infrared spectra that are available for these sources. Will they match? It's a very big question, I would say, but it's something we can test for and that we're starting to now put together.
And also related to this, I was wondering if the same geometry can produce, for example, variability in the infrared and not the X-ray.
Yes, so in the infrared, we don't actually see variability.
Okay.
What we see is a different spectral shape, I would say. So the proof in the infrared I was talking about before is essentially there's certain absorption features in infrared spectrum that if you assume that all of your dust is distributed in an homogeneous torus, don't really make sense. They're not fit very well by that model. But if you redistribute your material into clumps, then that fits your spectra in infrared a lot better. That's where the infrared proof kind of comes from. You wouldn't really see variability in the infrared because it's reprocessed emission rather than line of sight emission.
And concerning the 3D model, you showed at the end, you already have in mind some particularly physically motivated models or empirical ones?
Yes. So our starting point is, first of all, just a distribution of clouds, balls, which will have a distribution of density and a distribution of sizes. And then you can play with the broadness of this distribution, for example, and with your inclination angle.
Is this coming from some strong expectation, or is just simple to set up?
It's simple to set up, exactly, and it's the easiest way to reproduce. So this is being used at the moment to model infrared spectrum and X-ray spectrum. So using that in that sense, well, it makes sense, right, to see how wrong are we essentially with these simplified models that generate spectrum. For a more physically motivated thing, because at the end of the day, this is going to be a very well-behaved distribution that only rotates this way. We also believe that we can get direct simulations of a ready fountain, so like winds, into the skirt framework to try and do the same thing. So that would be the more strongly physically motivated model in that way. But in fairness, any simulation we could convert and use it. I would say that the issue might be finding the right simulations, right? So we're not going to do the simulations. We would like the simulation made already to put it in there. So if anyone has simulations in that regard, we would like that.
Okay, yes.
Very quick one. Even related to this modeling, I guess you will have many free parameters in construction of the model. Is there any way you can constrain some of them? I don't know, for instance, the inclination under certain assumption. Suppose you have, deep radio data for some of the objects that you can get some little jet, and that's a way to constrain, for instance, the inclination angle. Do you have a way to constrain the parameter space, or you will start exploring everything?
I think we need to start exploring everything. Yes.
Okay. That might be
yes,
difficult to conclude.
It may be difficult to conclude. I think that we're going to do things slightly separately. Like one thing is trying to explain non-variability. For example, I think it's a strong starting point because I don't believe every single geometry and distribution is going to be able to constrain that, right? So we're just going to start with a certain sampling of, cloud sizes, cloud distances, broadness of distribution. Can it be done? If the answer is no, can we play with the inclination angle? And then can it be done? The answer is no. What you have is that the clumpiness is a problem for some sources at least, right? So we'll go for more specific cases, and then we will try to constrain using this generic data, which we need to include all inclination angles, for example, because this comes from all of the source population. So in a way, your parameter space is reduced by the fact that you're including every inclination angle from the first place, right?
Okay, I see no remote questions, so we can thank the speaker.